A lot of times a set of data will have items in the set that occur more than once. In fact, some of the items in a data set may occur very frequently. Now, under that circumstance, where we have sort of a frequency associated with the items within a data set, our idea of calculating mean and standard deviation changed just slightly. Let's look at an example and I'll show you what I'm talking about. We're looking at there's a table over here, but it's a table involving the recovery times from shoulder injuries. Recovery times from shoulder injuries. Okay, here's the time X in number of weeks. And there are various patients. Some patients take 1 week, some take 2, some take 3, some take 4, and so on. So these are the number of weeks, the time in weeks it takes to recover from shoulder injuries. And this frequency column is the number of patients associated with this recovery time. So 5 patients required 1 week to recover. 8 patients required 2 weeks to recover. 12 patients required 3 weeks to recover, and so on. Now, if we were not to use the frequency table, think about what this would look like. If we have, if we're just listing recovery times now, we would have 1, 1, 1, 1, 1, 5 of them, you see. We would have 2, 2, 2, 2, 2, 2, 2, 8 twos. We would have 12 threes. We would have 19 fours, you see, and the list would be rather extraordinary. So using the frequency part of the table is kind of a convenience here. Now let's stop right here in the table, just with these 2 columns, and let's think about how our formula for mean might have to be changed to accommodate the frequency idea. Well, our idea of mean was calculated like this. Now, remember, mean is x bar. It's the sum of x values divided by the number of values. So the sum of all of the entries divided by the number of entries. And in our problem, it's the sum of the weeks involved divided by the number of patients. Now, how does that manifest itself? How do these ideas manifest themselves over here? The sum of weeks. Well, let's come back over here. We have, do we just add this column? No, because for a 1 week period, we have 5 of those. For a 2 week period, we have 8 2-week periods of recovery, you see. So we would have to add 1, 1, 1, 1, 1, 2, 2, 2, 2, 8 of those, and so on. So it's really the sum of, let's see, 1 times 5, 2 times 8, 3 times 12, you see. So we need another column that's marked XF, XF, and then total that, and we have the total number of weeks. And so this then is the sum of the weeks. It's the sum of XFs. Now, the denominator over there was the sum of the patients. Now, how many patients are there? Well, let's see. 5 patients required 1 week. 8 patients required 2 weeks to recover. 12 patients required 3 weeks to recover. These are the number of patients, the frequency column. So if we add the items in the frequency column, that is, we have a sum of frequency values, that turns out to be 60. That's the total number of patients. Now, so let's look back. Now, so this is summation of F. This is summation of XF for the total number of weeks. So let's go back over here and fill in. So the idea, sum of weeks, was the sum of XF. And the number of patients was the sum of the frequencies. That's really our N up here. Now, notice that the summation of X is replaced with summation of X times F. A lot of times in our formulas, in our 2 formulas, we're going to find out that to transition from or transition into the idea of grouped data, we simply tack on an F factor, you see, in a lot of the notation that goes on. And we'll see more of that when we get to standard deviation. But here, let's see, the sum of XF, the bottom of that column was 229. That's the sum of the weeks. And the sum of the patients, the summation of frequency values, was 60. And it turns out then that X bar is approximately 3.82. It's not so much the calculations here that we're concentrating on. We're trying to get the big picture or the concept of how to develop the notion of dealing with group data. All right, now let's talk about standard deviation. We're going to use one of the shortcut formulas for standard deviation. We're going to use this one. S is the square root of. Now, remember we talked about this earlier, and we're going to think about this in terms of the chart that we have over there. Now, the sum of x squared, remember from before, when we calculated standard deviation, we just needed two columns. We needed a column of x's, of all of the entries, and then we just squared each of those entries. And we took the sum of those squared entries to get this value. All right, what about x squares? Let's think about x squares in terms of what we have over here. Let's move back over and think about the x's being squared. Now, the x's, gee, the time x in weeks, do we just square these? Well, we could do it that way. The thing is, though, every one of these x's has a frequency associated with them. So if we square 3 to be added to other squared amounts, then we would have to add 3 squared 12 times. You see, so it's not just squaring these rascals and adding them. It's the idea of squaring these rascals and multiplying times a frequency. So we need a column that is x squared times frequency, and that's why I have an x squared f column over here. It is just for the purpose of calculating standard deviation. So x squared f. Now, it's the x squared. These are calculated by, let's come back over here. It's like 2 squared, that's 4, times 8, 32. 3 squared, 9, times 12, 108. That's how these are calculated. X squared f as it implies. And the sum in that column is the sum of x squared f values, which in this case is 1043. All right, let's go back over to the shortcut formula and see if there are any other surprises. Now notice that the sum of x squared is replaced with the sum of x squared f. Okay, the sum of x's all squared. Now the sum of x values, every one of those x's was associated with a frequency. So the sum of x is replaced with sum of xf, you see, and then that value is squared, and we have already talked about that. And the n, the total number of patients, was the sum of frequency numbers. So that's the sum of frequency as I have here. And this n also is the sum of frequency. And now we just replace. The sum of x squared f is 1043. The sum of xf's was 229, and that value is squared in the formula. The sum of frequency values is 60, and then 60 minus 1 in the denominator, and now it's a matter of punching the calculator. We find the standard deviation to be approximately 1.69, and that's and there is a unit associated with it. I should put the unit down here. It's some number of weeks. So it's the standard deviation 1.69 weeks. I should do the same thing with the x bar. This is the average number of weeks you see for recovery is 3.82, so it's 3.82 weeks for the unit. The Bureau of Land Management did a study of the water table near Custer, Wyoming in the month of June. Based on data from the BLM, a random sample of 20 water wells showed that the distance from the ground to the water level in feet is given by this chart. Now notice, distance to water, that's distance from the ground to the water level in feet. We'll call these x's. Now this number of feet, notice that this is a variable, this is kind of an interval, from 12 to 14 feet, from 15 to 17 feet. Now, how many wells fall into each of these categories? Well, here's the number of wells that fall into each of these categories. I've left a lot of space here because we're going to add something here in a moment, but I want you to realize that when the interval idea comes into play, and this is what happens when we're talking about classes and we're talking about histograms. When we want to make calculations about x bar and s, or mean and standard deviation, it could be mu and sigma, as you know, but at any rate, when we want to make some calculations about mean and standard deviation, we have to be talking about sum of x's, we have to be talking about xf's, we have to be talking about the sum of frequencies, you see, and stuff like that. So how are we going to add these x's? Well, there's not any single number here, and the actual depth of these wells is a variable amount between 12 and 14. It might be 12.3. The ones that fall out, 8 wells fall into this category, but one of them might be 18.1 feet, another might be 19.2 feet. But at any rate, all 8 of them fall into this category. Now, to accommodate the situation, all we do is we assume that we are going to only get approximations for the mean and the standard deviation. It's not exact because we have no exact information. But we can make a pretty good approximation for the mean and the standard deviation by taking the middle of each of these classes as our x values. That is, we'll create a column here, just midpoint. And these will be our x's, you see. And the midpoint of between 12 and 14, that's 13. And then 15 to 17 is 16. And then 18 to 20, that's 19. And 21 to 23 is 22. And 24 to 26 is 25. All right, now we have something meaningful, and we follow the same process that we followed on the previous problem. That is, we have a situation with group data here, and if you recall in that circumstance, now let's come back over here, and so that you don't have to rewind your tape, remember that we created 4 columns. We have a column of x values, we have a frequency column, we have an xf column, which is the product of these two, and then we have an x squared f column that is x squared times f, you see, or it's this column times x again. But at any rate, and we want the sums of those columns. Now, we're assuming here with these columns that we are using one of the shortcut formulas. If we're using kind of the long way of doing this, we can make columns involving the x minus x bar business. And we can talk about x minus x bar squares, you see, and the sum of those squared differences and so on. So we can go through that process as well, or instead of a process like this. It really depends on your teacher and what your teacher is asking you to do and which formula you are asked to use in this process. I kind of prefer the shortcut formulas myself, but at any rate, here we have a midpoint of all of these classes, and these midpoints incidentally can be selected if you have before you a histogram and you're just looking at the histogram and you're asked to give the mean and standard deviation. From the histogram, just look at the classes and just find the midpoint. You see, you want the midpoint of every one of those little boxes or rectangles, and that's really all there is to it. And then select those midpoints, multiply times the frequency. The frequencies are given by the height of each of those rectangles. So it's pretty easy to correlate the picture of the histogram with this kind of chart. Okay, so I've filled in, we've got the x, we've got the frequencies, I've got the sum of frequencies, we have the xf, we have the x squared f. Now we go through the process of calculating mean and standard deviation like this. I would suggest to you that to cut down on the memorization, you recall that the idea of mean is a total number of items by total of items divided by the number of items. And so you have that concept, and you might write this down. Now, we are using that concept in this specific area, you see, involving frequencies. So we know from our discussions here that we're going to multiply in a frequency idea in a lot of different places, so that as we apply frequencies, this becomes the sum of xf's. and this n, the number of items, is only the sum of the frequency numbers. And so now we have something that applies to what we have before us. And I'm suggesting that you flow through your logic like this so that you can think more in terms of big picture. You can think more in terms of concept. It's much easier to learn in terms of concept than it is to try to learn in terms of direct memorization. And oh, by the way, before I forget to mention this, we have a problem before us here, and I mentioned that we want to find the mean and the standard deviation. Anytime we're talking about a problem on the board and on the video program, and you wish to do this, then I would suggest that you do, and that is stop the videotape and try the problem on your own. Just gather enough information to work the problem on your own. Stop the video, work the problem, and then roll the video and see if you have gotten it correctly. And that way you can pick off where you might be likely to make mistakes on a test or on your homework, and make those corrections ahead of time. Anyway, let's go forward with this problem. The sum of the XFs, we just look at the bottom of the column there, it's 407. The sum of the frequencies was 20. There were 20 wells, you see. And then dividing, we find that the mean is 20 and 35/100 feet. So the mean depth for these wells is 20.35 feet. Now, standard deviation. Again, I'm using a shortcut formula here, and I'm using it in sort of a consolidated way. You know that this part, this numerator, can be designated as SSX. Remember that this is SSX, and a way to transition to this is to write it like this. It was actually n minus 1, but we're using as sum of f minus 1. But a way to transition would be to start here and go to that, and remembering that SSX is this business. Now, notice that I've already popped in the frequency, the little F designation here. And once you do this just a couple of times, once you go through this process just a couple of times, you will almost automatically say the sum of x squares. Oh, we're talking about frequencies involved in this problem, so let's tack on the F here. And here, this was the sum of x's squared, and then, oh, we're talking about frequency, so let's tack on the F, tack on the frequency. And the number, the n here, was the sum of frequency numbers, and here also an n was sum of frequency numbers. And now it's just a matter of looking at the bottom of the columns, and the sum of x squared f's from over here was 8,543. The sum of xf values 407, the sum of frequencies 20, and in the denominator 20 minus 1. Punching the calculator, we find that the standard deviation is 3.7 feet. Here's how you might use the graphing calculator to deal with grouped data. We would first press Stat and then Edit to enter the information. We're considering the same problem we had just a moment ago. Now, whether we're talking about group data where we have entries that have a certain frequency associated with them, or where we have a histogram where we have to identify midpoints, in this, let me get the cursor out of the way, these are the midpoints in L1 that we were talking about just a few minutes ago, and these are their frequencies. And now once these are entered, now notice L1 is the entries and the frequencies are in L2. And if we realize that, we press Stat, and now we want to calculate, press Enter because we want one variable stats. Now the protocol here is for us to enter the name of the list where our basic entries are, and then follow that with a comma, and then the name of the frequency list. So our main list is L1. Now I'm pressing second function number 1, which is L1, and then a comma, and now I want to enter L2, and that's second function on the number 2. So it's the basic entries are in L1 and their frequencies are in L2, and this tells the calculator where to go to find the information. Now we press Enter, and here's all the information for us. Notice the x bar, our mean of the sample, the sum of x values 407, the sum of x squared values 85, 43. These were numbers that would be used in our calculation if we were using our formula, and the calculator did the same thing, you see, to use the formula. This is the standard deviation of a sample. The calculator doesn't know whether we're dealing with a sample or a population. The sample standard deviation is this. The population standard deviation would be that. Let's see, n, the number of items is 20. I'm going to cursor down all the way here. N is 20. The minimum x value was 13. Maximum x value 25. The median for this group of information is 19. So we have an awful lot of information very quickly using the calculator. Let's calculate the coefficient of variation on the last problem. Recall that the mean was 20.35 feet. Standard deviation approximately 3.7 feet. The CV is S over X bar, standard deviation over the mean, times 100. Now I'm showing this problem because I want to emphasize accuracy in this kind of calculation. Recall that the standard deviation was approximately 3.7 feet. When we use an approximation and perform operations using the approximation, a lot of times we will increase the error in the approximation. And so to minimize the error in calculating CV, we might go to a more exact value for the standard deviation. So what I did is I backed up a few steps on the previous problem, and I found a step where I had an exact value for the standard deviation. Now this rounds to 3.7, but I don't want a rounded value. I want to use an exact value as I am making additional calculations here. So I use the square root of 260.55 over 19 for the standard deviation. The x bar was an exact value. It's 20.35 feet. And times 100, and I found this to be approximately 18.2%. Now this is still an approximation, but it's a closer approximation than it would have been had I used a rounded value here, or it could be a closer approximation. Okay, 18.2%. Now this means that the standard deviation is 18.2% of the mean in this particular problem. And CV, as you know, is just a measure of the spread of information relative to the average of the information. That's truly what it is.